Okay, this is my solution for the problem that we did on Tuesday of week 8. So the problem that we were doing this day was we were talking about induction. And the idea is that when you have a changing changing magnetic flux, and remember a magnetic flux is just B dotted with A. If you have a changing magnetic flux through a loop of wire, then an EMF is induced in that wire. And so for part A, it was a loop, and there's an external magnetic field that is increasing into the page. So that's definitely a magnetic field through some area of the loop. And so we have the magnetic field times the area of the loop. We were given the diameter of these loops. So it's pi times radius squared is area, so diameter over 2 squared. And that's the flux. For the second one, we again had a loop, and now it's decreasing out of the page. But that's actually the same flux, right? And then for part C, we had a loop that was actually where the plane of the loop was perpendicular to the direction, or I should say the area vector for the loop is perpendicular to the direction that the field is going. So there's no flux through the loop. It's not just any magnetic field in any area. There's no magnetic flux through the loop. So the magnetic flux in this case is 0. So the next stage then is to calculate what the induced EMF is for each of these, and we're going to calculate the derivative. Now the only thing that's changing in this case was the magnetic field, and so it's dB dt pi d over 2 squared, and of course the same over here. And so if you have an induced EMF, I should say, in a loop with some resistance, then of course you get a current. And so the current is equal to the EMF divided by the resistance. And so that's dB dt, which was given, times pi d over 2 squared divided by the resistance of the loop. And that's the answer. So of course the question is, how can they both be the same? We haven't said anything about direction. And so the direction is called Lenz's Law. And the book and most books put a minus sign in this law, which is called Faraday's Law. But I find that minus sign is not very instructive. So I remember it separately that the flux that is caused by the current itself. So there's actually two magnetic fields in this problem. There's the external magnetic field, and then there's the magnetic field that's caused by the current that's induced. And so in the first case, A, if it's increasing into the page, then that means that the loop itself tries to induce a current that has, in part A, flux out of the page. And when I put my thumb will have my fingers pointing out of the page if my thumb is pointing in a current that is counterclockwise. And this is a right-hand rule problem again. So for B, now if the field is decreasing out of the page, then the induced field is going to, well, look, again, make flux out of the page. And so it's again counterclockwise. Cool problem. That's the end.